Hey folks, got a couple, three examples of orbital mechanics. These are all going to be calculation examples, and I really urge you to try to actually use your calculator and get the same answers I'm getting. And if you're not, either let me know if the answers are wrong, or get help in how to actually calculate the right answers. So, um, in these kind of problems, I mean, there's two issues. One is knowing what to do, and the second issue is executing it properly using your calculator. All right, so we got a lot of big and small numbers here, so make sure that you're being careful. All right, so my first example, I'll just call it example A, is let's say you are standing on Earth and you want to throw a rock, and you throw a rock really darn fast. You throw that rock at a velocity of v naught is 5,000 meters per second. Darn fast, okay? Well, how high is the rock going to go? Okay, well, now we're going to ignore air resistance, which, by the way, wouldn't in reality be a good way to go here, but let's just pretend there's no air resistance and not worry about that. So you're going to use conservation of energy here, but we cannot use mgh because little g is going to change as the rock gains altitude. So our conservation of energy equation is, K naught plus U naught plus any work done by non-conservative forces equals K final plus U final. Okay. Now we're going to talk about after the rock has left my hand. So the work non-conservative will be zero. It's just the rock is just coasting upward. And when it gets to its max height, the final kinetic energy will be zero. Every other term has got a value to it because the starting height is not zero. The starting height is the radius of the Earth. Okay, so you can't say that's zero. So our equation will look like this. 1/2 mass of the rock, v squared, which we know, v naught squared, minus big G, mass of the Earth, mass of the rock, over r naught, which is the radius of the Earth, equals big G, mass of the Earth, mass of the rock, over r final. Now, what we want is we want the height above the Earth's surface that the rock reaches. We're going to solve for RF. That's going to be this here. So then once we find RF, we're just going to subtract the radius of the Earth from that to get the height that the rock gets above the Earth. Okay. Now, one thing you might notice is the mass of the rock cancels. That's still happening. It doesn't matter how big the rock is. Okay, so our values are for V naught, it's 5,000. Okay, we know big G is 6.67 times 10 to the negative 11th. Mass of the Earth is, we're going to use 5.97 times 10 to the 24th kilograms. R naught is 6.38 times 10 to the 6 meters. We're solving for our final, okay? So basically, what you're going to do here is plug and chug and carefully get our final, okay? And when I plug all these numbers in my calculator and solve for RF, okay, I get the following value. 7.978 times 10 to the 6th meters, okay? And then that's the distance from the center of the Earth to where our rock ends up at its max height. The height above the Earth's surface is RF minus radius of the Earth, okay? Which, when I subtract those, I get 1.597 times 10 to the 6th meters, okay? Now, again, if you don't get that value, A, make sure that I'm doing it right, and B, if this is indeed correct, or a friend of yours gets this right and you're not getting it right, please talk to somebody or me about how to get these in your calculator and how to actually correctly calculate them. All right, example 2, or example B. Okay. All right, so let's say that you are in charge of the International Space Station. All right. So we got the Earth here, and then here is the International Space Station. And right now, it's at a height of approximately 211 miles above the Earth's surface. And it's in, let's assume that it's in a circular orbit. Now, it's not quite in a circular orbit, but for the sake of argument, let's say it's in a circular orbit. And let's say you want to raise it to a new circular orbit that is 300 miles above the Earth's surface. Okay, so I want to know what is the work necessary to transfer circular orbits. Okay, so what's the work necessary to transfer from the lower circular orbit to the upper circular orbit? So we're still going to use conservation of energy. We got K naught plus U naught plus work non-conservative equals K final plus U final. Now, when we do this, we're trying to find work non-conservative. And where that, by the way, where would that come from? That would come from probably some kind of rocket fuel, okay, that you're burning. You're going to turn chemical potential energy into kinetic and potential energy. So we know that kinetic energy is 1/2 mv naught squared, and then potential energy is negative g mass of the Earth, mass of the station, over r naught, plus our work, equals, and then we got 1/2 mv final squared minus g mass of the Earth, mass of the space station, over r final. Now, it turns out that you don't have to do all this. Because we're going from one circular orbit to another circular orbit, I can shortcut this. We talked in the previous video about what is the energy of a circular orbit. When I add the 1/2 mv squared, v being root gm over r, because we're in circular orbit, you get this expression. Okay, so that's what we're going to do. So because we're in circular orbit, we can shortcut this and call this g mass of the Earth, mass of the space station, over 2r naught plus work equals negative g mass of the Earth, mass of the space station, over 2r final. Okay, and if I solve for work, and then I like to take some shortcuts. So what can I factor out of both these terms? G, mass of the Earth, mass of the ship, over 2. And all I'm going to do here is take 1 over r naught minus 1 over r final. Okay, so that's the shortcut. If you move this to the right-hand side, it becomes positive, and if you factor the GMM over 2 out, you get what's left and down below. Now, the values here. Okay, so mass of the Earth is approximately 5.97 times 10 to the 24th. Mass of the International Space Station is about 420,000 kilograms. R naught is the radius of the Earth plus the orbital height. So we need to add this plus that. Okay, so that's going to be 6.38 times 10 to the 6th. That's the radius of your Earth, plus 211 miles. And we got to convert that to meters, so we'd take it times 1609 meters in a mile. And then your R final is going to also be the radius of the Earth, 6.38 times 10 to the 6 meters, plus we want to be 300 miles above the Earth's surface, and multiply that by 1609 to make that into meters. So if you plug all those values in, I got the following answer: 2.60 times 10 to the 11th joules, which would equal 260 gigajoules. And it's just kind of fun to say. So double check my work, make sure that you actually get that number, make sure you can actually get that number, and check me to make sure I've got it right. Okay. All right, got one more example for you. Let's say that you are in the International Space Station. So here you are, okay? And we're 211 miles from the Earth's surface in a circular orbit. Okay, so we're orbiting as normal. And then for some reason you want to escape the Earth. Okay, you want to escape the Earth's gravity. So how much work does it take to escape the Earth's gravity from this circular orbit? Well, again, we're going to use conservation of energy. So we got K naught plus U naught plus the work non-conservative, which I'm trying to find, equals K final plus U final. Now, this is a total case of, if you know what to do, it's actually a very easy problem. Okay, So first of all, we're starting in a circular orbit. Okay, so because this is a circular orbit, these two added together will be negative g, mass of the Earth, mass of the ship, over r naught. 2r naught, sorry, 2r naught. We're trying to find work, so that's our W. If we're just escaping, so we're finding the minimum work necessary to escape. Well, remember what we talked about with escape. That means that as you're reaching infinity, your velocity is approaching zero if you're going the minimum speed here to escape. So when we get way out here, your velocity is approaching zero, so your kinetic energy is approaching zero. And your potential energy, which is negative gmm over r, well, if you make r approach infinity, that becomes zero. So your total energy should be zero, okay? Now that's, again, if you want the minimum work to escape. Of course, you can do more work than that, and then your total energy out here would not be zero. You'd have a velocity when you get to infinity, but we want the minimum. So you get a real simple expression here. You get the work done to escape, okay, is equal to g, mass of the Earth, mass of the space station, over 2r naught. And we already know those values from the previous example. Mass of the space station is 420,000 kilograms. Mass of the Earth is here. Our initial radius is this right here. It's the same stuff. It's 6.38 times 10 to the 6 plus 211 times 1609 meters height above the Earth's surface. When I plugged all those in, I got approximately 2.96 times 10 to the 7th joules, okay? Which is, let's see. A big number, of course. So there you go. So again, sometimes knowing what to do makes the problem a lot easier. All right, so I hope that example was helpful, and thank you very much.